Hello, good afternoon. So I know you're tired, but I will try to be as high level as possible. So first of all, thanks a lot to all of you for inviting me here, and thanks a lot for organizing this amazing workshop. Really, can we give us applause to the organizers, because they were amazing. Okay, now we're done with the applauses. I'm a researcher at Yahoo, and I'm a computer vision researcher. So what we do is to build intelligent systems to analyze visual data. And in this talk, I'm going to give you an unusual perspective about computer vision systems, because we're going to see the work that we have been doing at Yahoo in building machine vision systems that can estimate subjective image properties. So what we saw today and what we've been seeing in the past 4 years is that machine vision systems nowadays are able to detect with an impressive accuracy visible, tangible objects in image data like faces, dogs, cats, guitars, and so on. However, when we look at an image, we don't only see what is visible, because there is a whole world of intangible properties in subjective attributes that we necessarily attach to an image when we look at it, but we can't really see them. So for example, when I look at an image, I can say, oh, this image is beautiful, or this image makes me happy, but there's not an object that refers to sentiment, like there's an object that refers to a face. I can't really see the aesthetic value as I can see a cat, right? And so in the recent year, machine vision researchers, my colleagues, have been tried to model these properties using a computational approach. And to do so, computer vision knowledge, as we know it, should open up and borrows techniques and theories from branches of human knowledge that sometimes have nothing to do even with computer science. For example, anthropology, art, sociology, and so on. And so what I'm going to show you today is the work that we have been doing at Yahoo Labs to bridge computer vision and break the boundaries of computer vision, to bridge it with these disciplines that we see here and estimate subjective image properties. So one of the branches of subjective machine vision that have been widely explored by myself and my colleagues is called computational aesthetics. And what we do in computational aesthetics is to build vision systems that can automatically assess the photographic beauty of images and videos. And we do so by teaching machines, given a few examples, a lot of examples of images annotated with aesthetic degrees, and given some visual features encoding photographic rules, how to distinguish between good and bad pictures. Now, what we do at Yahoo is that we tackle a particular problem in computational aesthetics, because we focus on a narrow image domain that is the domain of portraits, so images with faces only. So ideally, we want to build systems that, given a portrait, are able to estimate the photographic beauty of this portrait. We don't really care whether the person depicted is beautiful or not. We are not looking for this aspect. We want to know whether the image composition is beautiful, knowing that there is a person in it. Now, you might ask, if we already have computational aesthetic frameworks out there, why would we need a specific computational aesthetic framework for faces? So if you know computer vision researchers, they tend to put the sentence, an image is worth 1,000 words everywhere, every 2 words, right? And so what I always say is that if an image is worth 1,000 words, a face image is worth an entire story. Because face image portraits typically depict people, and people come with all their problem of being human. So their emotions, their lifestyle, their history, and so on. And so photographers, portrait photographers actually should follow specific rules when depicting people, because they have to vehiculate the humanity of the subject. And so portrait photography is actually a separate branch of photography. And given this, we thought that we should build a separate portrait aesthetic framework, different from general computational aesthetic frameworks. And to do so, we collect a large collection of pictures annotated with aesthetic degrees by professional photographers. And then we reduce it to a face-only image dataset by running a deep learning-based face detector on it. And then we build on the output of this deep learning face detector to design a set of visual features inspired by portrait photography. This means that we read and we dig into portrait photography literature, and we map each of the rules that photographers should follow to shoot good portraits into a visual features, into a computational approach. And then we feed a machine learning algorithm that we saw yesterday, a random forest, with the visual features and the annotations. And this system will learn how to distinguish between good and bad portraits. Now, here is a plot of the results. This doesn't really say much apart from that this system works pretty well for the aesthetic scoring of digital portraits. And also it tells us that this system works much better than general computational aesthetic framework. And this justifies all the effort that we did in designing a specific framework for faces. And the nice thing about this framework is also that because we specifically design each of the features on top of the deep learning detector to map photographic rules, we design these features that are interpretable. So when we look at how the machine behaves when distinguishing good and bad portraits, we can also understand what makes a portrait beautiful from an algorithmic perspective. And so we can see that there is a whole group of features that positively correlate with portrait beauty, such as, for example, technical things like the sharpness of the landmarks of the faces, or the originality or the uniqueness of the composition. There is a whole group of features that are negative indicators of portrait beauty, such as, for example, the excessive use of color or the excessive balance in the exposure, because photographers should play a bit with the exposure to vehiculate the subject emotions. And then there is a third group of features that actually does not correlate at all with our target variable, with portrait beauty. And you, in this audience, I guess you know how much it's frustrating when things don't work, right? When features don't correlate, they don't have signals. But here, we have a nice message, because this tells us that no matter the age, the gender, and the race of the person depicted, if the photographer does a good job in vehiculating the subject emotions and a good artistic job, then the resulting portrait will be beautiful. So in the context of computational aesthetic, I'd like to show you another work that we've been doing with my colleagues at Yahoo Labs in the context of Flickr. So as you might know, Flickr belongs to Yahoo and is a very large photo sharing platform with millions of users and billions of pictures. Now, what happens in Flickr is that only a small percentage of these billions of pictures are actually accessible from the final users. And these are typically the most popular pictures, because popular pictures spread easily around the social network, and they are simply easily retrievable. And as a result, the vast majority of Flickr picture is actually not accessible by Flickr users, or not easily accessible, because there's no social signal on those pictures, and so users have really to dig into the network to find them. And so with the aim of promoting good quality content to our Flickr users, together with my colleagues at Yahoo Labs, we ask ourselves, is popularity a good proxy for quality? Are all the beautiful pictures in Flickr lying on the surface of popularity? So we ran a crowdsourcing experiment asking users to annotate the beauty of thousands of Flickr pictures. And the result of this experiment is that, yes, many popular Flickr pictures are actually very beautiful. But yes, there is a large number of beautiful pictures lying under the surface of popularity that nobody can see, because they have no social signal. And those are what we call the hidden gems, because this is very high quality content that is hidden to the final audience. And so with the aim of surfacing those hidden gems and providing our users with good content, we employed a computational aesthetic framework. So what we do is that we take a very large data set of completely non-popular Flickr pictures, and we score their beauty with a computational aesthetic algorithm. And then we rank the pictures according to the predicted score, and at the top of this ranking, we will have the most beautiful pictures among the non-popular pictures in this data set. And those are what the gems that we were looking for, right? Because those are supposed to be very beautiful pictures, but unpopular. So because we can't fully trust the subjective machine vision systems yet, we go back to the crowd and ask for a validation of this experiment. And we were very happy to see the results because this plot tells us that these automatically surfaced pictures are non-popular, but are as beautiful or even more beautiful than the most popular Flickr pictures. And here at this link, you have all the data set with all the annotations. If you want to take a look at it, please contact me. We are very happy to share our research. Here I put some examples of the surface gems. Unfortunately, you can't see them very well, but those are very beautiful pictures. And they have almost zero likes or favorites on Flickr, right? So those are very unpopular. And this would not be visible to me, to you, and to the Flickr audience if we didn't have a machine vision algorithm surfacing them for us. OK, so, and because we were very happy about our results in subjective machine vision, we decided to push a bit the boundaries of subjectivity and explore, under a computational approach, the even more subjective notion of creativity. And to do so, we focus on an online microvideo photo sharing platform called Vine. I don't know if you know Vine, but this is a microvideo sharing platform that was acquired by Twitter 3 years ago, and that allows users to create and share videos with a maximum length of 6 seconds. Now, what happened with Vine is that the visual artist community and the motion graphic artist community actually realized how much Vine would foster their creativity. And this was due to the fact that this 6-second constraint was broadening so much their imagination and their creativity. And so Vine is a platform very much related to the notion of creativity, but there is a small problem. As many online environments, not all Vine videos are creative. And actually, 99.9% of the videos look like this one, like the cat one. While we would like to see more of the creative videos, like the cherry one. So together with my colleagues at Yahoo Labs, we decided to build a machine vision-based system that can automatically discover creative Vine videos. And to do so, we had a couple of problems. First of all, what is creative? Right? So creativity is a notion that has been explored pretty much by any branch of the human knowledge, from mathematics to philosophy to computer science. So we had to dig into the literature and of the definition of creativity, and we finally came up with a shared definition where something creative is an artifact that has some novel aspect, but also has some benefit, some value for the final user. And then stemming from this definition of creativity, we designed some audiovisual features that can model both novelty and value in order to teach a machine how to recognize creative videos. And so through audiovisual features, we can model both value, the aspect of the final benefit for the user through aesthetic and affective features, but also using some multidimensional clustering technique, the novelty of our microvideos. And then there was a third problem, that there is no ground truth out there to teach a machine how to distinguish between creative and non-creative video. So again, we go to the crowd. We design a crowdsourcing experiment asking users to annotate the creative degree of around 4,000 Vine videos. And then having the annotation and having the features for the videos, and we can teach a machine how to distinguish between creative and non-creative videos. Again, this dataset is available online at this link if you want to take a look at it. Now, we were very surprised about the outcome of this experiment, because this system is able to detect with 80% of accuracy the creative degree of the Vine videos in the dataset. And again, here, unfortunately, due to time, I cannot talk too much about it. Because we carefully designed the features to be interpretable, we can also understand what makes a video creative from an algorithmic perspective. We can talk more offline about all these patterns that we discovered if you want. So as a last part of this talk, I'd like to show you a work that I really like, and it's a very new work that we have been doing with an amazing team of researchers around the world. And it's about estimating one of the most subjective dimensions of humanity, which is sentiment. What is more subjective than sentiment? Like, think about love. If I was asking you to put love into pictures, probably each of us would assign different visual concept to this emotion, right? And this depends very much whether we had a good or bad day, whether our history, our background, our cultural background, and so on. And actually, emotion perception is very subjective, and myself and my colleagues have been trying for years to estimate automatically the values of image sentiment using computer vision approach. But what we often forget is that not all users are similar. We tend to treat users of online photo sharing platform as single monocultures, but each of the users is very different. There is a high diversity among users. And on top of that, what anthropology tells us is that one of the main factors impacting our emotion perception is the cultural background where we grew up. And so we team up with this amazing team of researchers from various institutions, including Columbia University, IBM, EPFL. They are very multicultural and multidisciplinary. And we came up with this framework that would allow us and the whole community, and also you outside the community, to evaluate from an algorithmic perspective the impact of culture in visual emotion perception. So with this framework, we want to answer a couple of questions that psychologists have been struggling for ages. Maybe it's a bit too ambitious, but still, we're working on that. Like, for example, how similar are different cultures when expressing visual emotion, how different are emotions when attaching sentiment to pictures, and so on. And so to do so, the first step to achieve this ambitious goal is to collect a large data set that would allow us to explore computational techniques to address these problems. And so we built this data set called Multilingual Visual Sentiment Ontology that is available at this link. So this data set contains more than 7 million Flickr pictures spanning users from 12 different languages. And each image is annotated with the language of the user that uploaded the picture, with a positive, negative sentiment value arising from sentiment analysis of the metadata, and with some emotion keywords that tend to highly occur with the tags in the image. So this dataset, again, is available online. Please contact us if you're interested in exploring this problem. Then we have a mailing list, and the people in the team are amazing, so don't hesitate. So just a few words on how we built this dataset. So this was the first time that someone in multimedia computer vision community tried to build something like that. So we had to build an ad hoc pipeline that starts with the plastic wheel of emotions, which is a set of 24 emotion keywords organized according to psychological properties, and then uses them to query Flickr, pull in the metadata, polishing it with the hell out of natural language processing, crowdsourcing, visual analysis, and so on. I'm going to skip the details, but the resulting data set is a somehow reliable data set that can help the community explore this problem. And in this context, I think I'm running out of time, but I'm going to just show you one of the experiments. It's a very simple experiment that we did in this context, which is about comparing sentiment models from different cultures. So what we do for this experiment is that we take 6 of the major languages in our corpus, and for each of these languages we build a language-specific visual sentiment predictor. And then we use this language-specific sentiment predictor to predict sentiment of images in other languages, to perform cross-lingual sentiment prediction. And by looking at the performances of cross-lingual sentiment prediction, we can understand how different languages are similar when expressing sentiment in their images. To do so, here it's this part over there contains basically everything that was explained this afternoon, so I'm going to skip this. But the idea is that for all the images that we have in one language, we process them through an AlexNet type of deep learning framework. And based on some positive negative sentiment annotation, the network, given an image of that language, is able to output a positive negative sentiment value, is able to predict a positive negative sentiment value just by looking at the pixels. So those are the results for these 6 languages. We can't really compare with anything else in literature because this is the first time someone builds language-specific visual sentiment detectors. But the idea is that, well, they work much better than random, and also that the performances are much better than previous visual sentiment analysis tools. But the thing that we can do with this language-specific sentiment detector to understand to which extent they perform well is to perform cross-lingual sentiment prediction. So the idea is that we want to predict the sentiment of the images in a given language, given the sentiment detectors trained on other languages. And by looking at how much this cross-lingual prediction performs, we can understand whether languages are similar or different. So those are the aggregated results. These are not very well understandable, I know, but this says that basically language-specific detectors are much more performing than cross-lingual detector, which justifies the fact that we embed the language information into visual sentiment detection. And then we can spot some nice patterns. So for example, the language whose sentiment is most difficult to predict given detectors trained on other languages is Chinese. And this is probably because in our pool of languages, Chinese is the only Eastern languages versus all the others that are kind of more European Western languages. But also, we can see that among Latin languages, cross-lingual prediction performs very well. So for example, it's very easy to predict the sentiment of Spanish images given the sentiment detector trained on Italian images. Okay, so I think I have to conclude. So these findings and many more that we have in our research tells us that computer vision is a very powerful tool to understand under an algorithmic perspective how we behave when perceiving the visual world. And I want to stress the fact that a lot of effort have been put in our work to design feature experiments and algorithms that are interpretable and that can tell us something to humans, because this is the only way in which we can actually learn from the machines and understand under an algorithmic perspective how we perceive the visual world. And with that, I want to also thank all these people that without them, all this wouldn't have been possible, and all of you for listening. And